Hello everyone, welcome back to Spectrum Classes. In this video, we are going to discuss molecular orbital diagram for diatomic molecules. In my previous video, I have discussed the wave mechanical treatment for molecular orbitals, and here we are going to discuss the molecular orbital diagram. So that is the difference between these two. And now we will start with a video. Homodiatomic molecules. So what is written over here? First we must know the meaning of this. So homo means same. Di means two. Atoms, when combined together to form a molecule, those are known as homodiatomic. Say, for example, here one hydrogen, second hydrogen, these two combine together to form hydrogen molecule. So this is called homodiatomic molecule, right? In the same way, we can write down He2, B2, and N2, oxygen, fluorine. These all are homodiatomic molecules. I hope you understand here. Now, in this video, we are going to discuss how to draw these molecular orbital diagrams and what are the important points which needs to be considered and their basics from where they are originated, right? And how these bonding and anti-bonding molecular orbitals are designated, like I have shown here, sigma bond and sigma star. So these are the important points, and here how this p orbital combine together to form sigma as well as pi molecular orbital. So here are the few basic steps which needs to be considered while we are drawing the molecular orbital diagram for diatomic molecule. And write down its electronic configuration. Electronic configuration for this hydrogen atom is 1s1. Now you need to draw atomic orbitals with their electrons in increasing order of energy. So here I am just writing, since we are having one orbital only, one orbital is there with us, so we will just draw these 1s orbitals in this manner first. Now moving ahead, these are the atomic orbitals, right? Moving ahead, now we are going to consider the overlapping of these orbitals and what kind of molecular orbitals are formed by combining these atomic orbitals. So that we need to consider, and here we are forming the molecular orbitals. So you can see here, this is the energy level of these atomic orbitals, and here is the bonding molecular orbital, which is lesser in energy than the atomic orbitals. And here is the anti-bonding molecular orbital, which is higher in energy than the corresponding atomic orbital. Right? This thing about the energy we have already discussed in our previous video. So if you didn't check that video, please go and check that. Right? Now coming to the filling of electrons. So filling of electrons in these orbitals follow the Aufbau's principle. What is that Aufbau's principle? Electrons are filling in increasing order of energy. Second, Hund's rule of maximum multiplicity. So what is this Hund's rule of maximum multiplicity? When we are having more than one molecular orbital at same energy level, then we will fill them singly first and then pairing will occur. So that is the Hund's rule of maximum multiplicity. And the last one is Pauli's exclusion principle. It means as we did in the same orbital, two electrons cannot occupy the same all four quantum numbers. Electrons are paired up in the same orbital, right? So these are the three important rules which needs to be followed. Formation of helium molecule. So helium molecule, first what you need to do, you need to write down its electronic configuration. So it is having two electrons, so 1s2. Now draw the atomic orbitals in their increasing order of energy. So since we are having only 1s orbital, so 1s orbital is drawn like this. And then we are having overlapping of these orbitals to form molecular orbitals. So overlapping means overlapping of same symmetry and of almost or similar energy for atomic orbitals combined together to form molecular orbitals, that I will explain. So here we are having these bonding and anti-bonding molecular orbitals now filling the electrons here. So this filling of electron I will discuss in the next slide, right? So first we are going to discuss how these molecular orbital diagram is formed. So suppose this is the hydrogen atom, and this hydrogen atom is represented like this. So this is having one s orbital, and this is one s orbital of another hydrogen atom. This is one hydrogen atom, and this is second hydrogen atom, its nucleus. Suppose we are having a wave. The electrons which are present here, that can be represented by electron waves, and these electron waves can be represented as a wave function psi a. So this amplitude of this wave is represented by with this psi a, amplitude of this wave. Now the second wave of the another hydrogen atom is having the amplitude psi b, and on combining these, when these are in same phase, we will get an amplitude which is equal to psi a plus psi b, and this psi b represents the bonding molecular orbital. This small b is equal to bonding molecular orbital, right? These are showing the constructive interference. So this is what you can see here, and if we see the probability of finding the electron, then in this case we are having psi a square, for this psi b square, and for this we are having psi b square. So what does this psi b square means? Psi a plus psi b square, right? So on expanding this, we will get psi b square is equal to psi a square plus 2 psi a psi b plus psi b square. About this term, I have discussed in detail in my previous video, so you can go and check there. But here, why I have explained it again here, because in several textbooks or in class 12 textbooks, this linear combination of atomic orbitals is given in this form only, right? So you can understand here. If these are in constructive interference, it means, so here these two s orbitals combine together, and here plus plus signs are there, means they are in same phase. This gives us bonding molecular orbital, and this s and s orbital overlapping will gives us sigma bonds. So here this bonding molecular orbital of s overlapping is designated as sigma bonding molecular orbit. Now I'll show you the destructive interference. So suppose in case of destructive interference, suppose for one hydrogen atom we are having the wave in this manner and with amplitude psi a, and the other wave is in this manner or in opposite phase with amplitude psi b, and on adding these two we will get a resultant wave having amplitude in this way, right? So here the important point is that if we are having psi a is greater than psi b, means this amplitude is more than this amplitude, then on subtracting these two, what kind of response we will get? We will get a response like this, right? If psi b is greater than psi a, then it means psi b downward amplitude is more. So what kind of resultant response we will get? We will get this kind of response. If both psi a is equal to psi b, then we will not get any kind of response, means zero amplitude. So these three kind of responses we are getting depending on the conditions. Here I have shown you one type of result, and the amplitude of this wave, resultant wave, is represented by this. Here psi a and psi b, and this psi a represents the antibonding molecular orbital. So here you can see, if we see the probability density of electrons, then psi a square is equal to psi a square minus 2 psi a psi b plus psi b square, means the resultant wave is lesser with this term. Now I will show you the formation of, this is constructive interference which we have discussed in the previous slide, and here we are having the destructive interference where antibonding molecular orbitals are formed. So here constructive interference or overlapping is shown by the plus plus, and here it is shown by the plus minus, as you've seen here, right? So here is the repulsion, and this is called internuclear axis, internuclear axis, and on destructive interference, a sigma star antibonding molecular orbital is formed by these SS orbital overlap. So this is how the sigma and sigma star are formed with low and high energy. Now I will draw the molecular orbital diagram for this helium atom. So here I will show you. First you just write down the electronic configuration in the second step. And since we are having one orbital only, so I have drawn one orbital here. On first do this kind of exercise. Here is the energy, and this is my first atomic orbital, and this is my second atomic orbital, right? This is atomic orbital, and this is 1s atomic orbital, 1s atomic orbital. It is having 2 electrons, so fill 2 electrons here in this manner. Now you see the overlapping of this s and s orbital. So by the overlapping of s and orbital, what we will get? We will get a bonding molecular orbital, and other one is antibonding molecular orbital. So here, this is what I have drawn here, right? Now coming to the number of electrons which we are having. So altogether we are having 4 number of electrons. Now we are coming to the third point, how to fill these electrons in the bonding molecular orbital. So these 4 electrons are filled in the bonding molecular orbital and antibonding molecular orbital one by. Since the energy of this bonding and antibonding molecular orbital is different. So first we will fill the bonding molecular orbital with electron number 1, electron number 2, and then electron number 3 will go there, electron number 4. Here I have just designated these electrons in this manner so that it will be easy for the students to understand how these 4 electrons will be filled in the molecular orbital. Now I will show you the filling of electrons. So electron number 1, 2, 3, and 4. This is how electrons are filled. Now coming to the writing of electronic configuration for these molecular orbitals. So how you are going to write the electronic configuration? So here this is the sigma, as I told you earlier. How the sigma is formed? This is formed by the overlapping of s and s orbitals, right? So this sigma is formed by the 1s orbital. So this is sigma. It is formed by the overlapping of 1s orbitals. And how many electrons are present in this sigma orbital? So 2 electrons are present. Now place the comma, move to the higher energy orbital. So this is my next higher energy orbital. So how it is designated? It is designated as sigma star. And how it is formed? It is formed by the overlapping of 1s orbitals. So this is 1s orbital. How many electrons are there? So 2 electrons are there. So this is the electronic configuration for this helium atom. If you find it difficult here, I will elaborate it in the upcoming example. So you need not to worry here only. Now coming to the calculation of bond order. Bond order means how many bonds are present or how these two atoms are connected with each other, right? So this bond order is equal to 1 by 2 brackets number of electrons present in bonding molecular orbital minus number of electrons present in anti-bonding molecular orbitals. So you can just write down here. Now up to this, I hope you understand. Now coming to this 2, from where this 2 comes? So this 2 comes from here, right? This is the bonding molecular orbital. So 2 electrons are present in the bonding molecular orbital minus how many electrons are present in the antibonding molecular orbital? So 2 electrons are present in the antibonding molecular orbital. So here I have written number of electrons present in the antibonding molecular orbital. Since this 2 minus 2 will gives us 0, so 1 by 2, 0 will gives us again 0, right? So I have elaborated it here. So bond order helium 2 molecule is 0. It means there is no bond between helium and helium. Therefore, what kind of inference we have made out of this? Helium molecule doesn't exist, right? Now coming to the next example. So next example is with lithium. So what I said first write down the electronic configuration of the atom for which you need to write the molecular orbital diagram, right? So for lithium too, you have to write down the molecular orbital diagram. So write electronic configuration of this lithium atom. What is the use of writing this? So this is 3 lithium, 1s2, 2s1, right? So the use of writing this is that we can arrange the atomic orbital in increasing order of energy. Now here you can understand how we are going, what does this mean? So here is the energy, and this 1s has lesser energy as compared to this 2s1 energy, right? So 1s2 written first and then 2s1 written afterwards, right? So I hope you understand here what does it mean. Now next, draw the molecular orbitals. So s orbital combine together to form, how many atomic orbitals are there? 1, and 2 s orbitals are combined together. So as many atomic orbitals are combined together, they will form same number of molecular orbitals. So two atomic orbitals combined, they will form two molecular orbitals. 1s will combine together, they will form two molecular orbitals. One is sigma and the other one is sigma star, as I told you earlier in my previous slide. So here what we get? We get sigma, and here you can see sigma orbital and sigma star by the overlapping of s and s orbital. Here this is sigma orbital and this is sigma star. In the same way, this 2s atomic orbitals. So two atomic orbitals combine together to form two molecular orbitals. Here I will show you this one molecular orbital and this second molecular orbital. Now, by the combination or by the overlapping of this s and s orbital, we will get sigma and sigma star orbital. So, if you have any doubt, then I will also continue it with the next example, right? Now, in this manner, you have to draw your molecular orbital diagram. Now, how many electrons are present? So, here one lithium atom is having 3 electrons altogether. So 2 lithium atoms, how many electrons are there? So 3 into 2 or 3 plus 3, we will get 6 electrons, right? So here you can also calculate in this way, or you can calculate it in this way. 2 electrons were there, 1 electron was there, 2 electrons were there, 1 is and 1 electron. So how many electrons are there? Total 6. 4 I have written here, and these 2 I have written here, right? So in this manner, I have collected all these. I can show you here. Just see. So all these 6 electrons we have separated at this place, right? Now fill up all these electrons in the order. What kind of order we need to follow this? Electron number 1, 2 out of 6 electrons, right? Electron 1, 2, then 3, then 4, 5, 6. This is the correct order. So 6 electrons you need to fill in this way. Now you can see here how these 6 electrons are filled. So which place will go to which place, that doesn't matter. And we have to fill 6 electrons all together in the increasing order of energy, right? So this is how one can draw the molecular orbital diagram for lithium 3. Now write down the electronic configuration. So are you be able to write the electronic configuration for this? So this is sigma. How it is formed? It is formed by the combination of 1s. This is sigma star. Sigma star is sigma star, and this is formed by 1s orbitals. Next is sigma orbital. Here you can see the sigma and how it is formed. It is formed by the combination of two s orbitals. This is sigma star. Here you can see. So increasing order of energy you need to follow. How many electrons are there in sigma 1s orbital? 2 electrons. You just see here. In sigma star, we are having 2 electrons. In sigma 2s, we are having 2 electrons, and this is vacant. So no electron I have written here, right? So this is how you can write down the electronic configuration for molecular orbital diagram. Now coming to the next, how to calculate the bond order. So bond order is equal to 1 by 2 number of electrons in bonding molecular orbitals. Here I will show you the bonding molecular orbital. So these are the bonding molecular orbitals, which are represented by the stars that are anti-bonding. And here you can see the anti-bonding molecular orbital. This is the anti-bonding molecular orbital. So 4 electrons in the bonding molecular orbitals and 2 electrons in the anti-bonding molecular orbital. On solving this, we will get the bond order is equal to 1. It means lithium is having one bond in between, right? So you just see lithium is in this way, right? Now coming to the magnetic property also. So what is the magnetic property? If magnetic property can be interpreted by the number of electrons present in the molecular orbitals. The last electron which is filled over here in this way, right? So if they are paired, then this is diamagnetic, and if it is unpaired, it is paramagnetic, right? So paired, the trick which I follow for this, diamagnetic means here I just have a trick for this. So dia means 2. So if 2 electrons or paired electrons are there, it means it is diamagnetic. If unpaired electron, 1 electron is there, unpaired electron is there, then that is called paramagnetic, right? So this is how one can predict the magnetic pair. So lithium is diamagnetic in nature. Now coming to the next example, here is the beryllium. Now first write down the electronic configuration for the beryllium atom. So here 1s2, 2s2. Draw the atomic orbitals in the increasing order of energy. 1s2 here, 2s2. This is 2, right? So 1s2, 2s2. So 2 electrons are there filled. 2 electrons filled in this, 2 electrons filled in this, and this also, right? So now moving to the filling of electrons. So we will collect all these electrons. So how many electrons are there altogether? 4 electrons are here and 4 electrons are there. Means we are having 8 electrons. So how to fill these electrons? What will be the order which needs to be followed? So electron number 1, 2, 3, 4, 5, 6, 7, 8. So this is how we need to fill the electrons out of these 8 electrons, right? So we are going to fill, just see this, and these all are paired, right? So they follow the Pauli's exclusion principle. Now coming to the writing of electronic configuration. So how to write the electronic configuration? Sigma 1s, comma, sigma 1s star, comma, sigma 2s, comma, sigma star 2s, right? This is 2s. And now write down the number of electrons present in these orbitals. So 2 electrons, here you can see 2 electrons, 2 electrons, and 2 electrons here. Yes. So this is how one can write down the electronic configuration for molecular orbital, right? Now coming to the bond order. So bond order can be calculated by this formula, 1 by 2 number of electrons in bonding molecular orbital and number of electrons in antibonding molecular orbitals. If you forget how to memorize this, so bond order starts with B, So bonding molecular orbital, then we are having the antibonding molecular orbital. And since these two are bonding and antibonding, divided by 2, right? So this is how you can connect your formula if you somehow forgot. Now count the number of electrons present in the bonding molecular orbital. So this is our bonding molecular orbital. Again, this is our bonding molecular orbital. So how many electrons are there in the bonding molecular orbitals? Altogether, they are 4. Now coming to the anti-bonding molecular orbital. So this is our anti-bonding, which because it is high in energy and designated by star. So 4 electrons are again there, right? So 4 minus 4, we will get 0. So beryllium 2 doesn't exist. Useful? Then please like, share and subscribe. Thank you all. Thanks for watching.